Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be continuing our work on partial fractions, and in particular, we'll be looking to express more challenging sort of fractions into partial fraction form. So before we jump in with sort of new content, new material, let's just take stock of something rather important that we actually saw last time, which was when we're writing down partial fractions, we need to know, given a description of an expression or a fraction rather, what the general partial fraction form is going to be like before we actually start to do any algebra. So in particular, if we have something like px plus q over, say two linear factors, then the general partial fraction form is just going to take each one of these linear factors and make a fraction using those sort of factors as independent denominators. And then the numbers in the numerators are going to be things that we're going to have to find out, right? But of course, if we had the case where we had px plus q with three linear factors, then the general partial fraction form will have three separate fractions, and each denominator in each of these fractions are just going to be the factors that we actually had written out independently, and then we're going to have three sort of numbers in the numerator that obviously we're going to have to do some work and find out. We also saw, in fact, that we can have the denominator of our initial expression that we want to express in partial fraction form to not be a linear factor, but to be a quadratic factor. And when we had a quadratic factor, we sort of reasoned our way and figured out that actually, if we sort of have anything other than something which is different than what I've got on the right hand side here, then things start to fall apart. So what do we need? We actually need something like two separate fractions, of course, because otherwise the thing on the right hand side won't really be a partial fraction. It will just be one fraction, right? So we need at least two for it to be a partial fraction, and then we need two denominators, but the denominators are going to be, it's going to be the exact same factor we actually had on the left hand side, but we're going to have two copies of it once and then just one copy of it, right? And but the numerators can just be constants that we're going to sort of figure out later. And lastly, we also saw that we could have a case where we've got sort of a linear function on top, so px plus q, but the denominators have two factors, but one of the factors is actually a quadratic factor that cannot be further factorized. So I've got to stress that. So we've got cx squared plus d, and in this case we're saying if cx squared plus d does not have any further real factors, then the general partial fraction form is going to look like this, which is you're going to take the first factor, the linear factor, you're going to put that down. Then you're going to take the quadratic factor, which cannot be further factorized, and you're going to put that down. But the numerator of the quadratic factor is not just going to be a number, it's actually going to be a linear function, right? And why is this? Because ultimately, either you can just remember this, but ultimately there's a heuristic working in the background, which is as long as all our partial fractions are of the form where the order is one less on the top than it is on the bottom, then the thing is going to work out for us. And of course, by order, I just mean the degree of the polynomial. At this stage, I should say, you might come and say to me, hang on, the third sort of case we've got here, of the sort of four different cases I've written down, the third case, the right-hand side, the second term, has the denominator is of order 2, but the numerator is of order 0, so it doesn't quite fit this rule. We discussed this sort of a case precisely in the previous video, and we showed that actually writing it in this form is perfectly mathematically and algebraically consistent with writing it in a form where I had, say, a bx plus c on top here, right? If you want sort of more information on this, do go back and look at that video. Now, the only other point worth mentioning is the four cases that I've broken down the general partial fraction descriptions into can actually come with sort of special cases where you can sort of pick special values for either P and Q, or you can pick special values for A and C, and then we sort of get other cases. But the point is, in all these other cases, the general partial fraction form is just going to be the things that we've already got on the right hand side for each case respectively. So there's nothing new in that regard. So let's jump into the sort of content for this video. So in this video, we're going to be actually expressing improper fractions. So improper fractions, ultimately to partial fraction form. However, the difficulty is the best way of actually being able to do this, to go from improper fractions to sort of partial fractions, is to actually convert the improper fraction to proper fraction and then to go from proper fractions to partial fractions. Now, here's where our knowledge of polynomial division becomes important, because to be able to do this first step, to be able to go from improper fractions to proper fractions, we actually need to be able to divide polynomials, right? So what do I mean by that? I mean, say f of x is some polynomial, and p of x is some other polynomial. So you've got a fraction, which is an expression with something on the top and something on the bottom, right? And of course, this is top heavy, or another way of saying this is improper, improper, if the order of f is actually bigger than the order of p. Now, some people use the word degree rather than order, but both those things really mean the same thing. So an example of this might actually be something like, say, x squared plus 5x plus 2 divided by x plus 1, right? So this is improper, this is top heavy, whereas if I had something like x plus 1 over x squared plus 5 x plus 2, so the first one is top heavy, uh, or as I say, improper, but the second one is actually proper. And that's quite clear why that is. This one has order 2 on the top and order 1 on the bottom, or the degree is 2 for the polynomial function on top, and the degree is 1 for the polynomial function at the bottom. And the other one is the other way around, so it's actually not improper. This one is actually proper. Let me make a bit of room and continue with the argument I'm making. So the point being that when we actually have a sort of an improper fraction, what we can actually do is we can actually carry out a long division. So I can put the thing I've got to divide by here, I put the thing that I'm dividing by here, right? I carry out a long division, and in the end, I end up with some sort of a remainder. And of course, the thing on the top is going to be my quotient. And generally, the way we express this is we know that we're going to take f and we're going to divide it by p, and we're going to end up with a quotient. And then we're going to have obviously our remainder, which is what's left over, something that we can't get rid of any further. But of course, we've not quite finished the division, so the division has to carry on. So the statement I've now written on the right-hand side is basically a generic description of what happens when we actually start to divide polynomials. Now, an equivalent way of writing this is actually to be able to say something like this, that if I have a function f of x, I can actually say it's going to be q of x times by p of x plus r of x, right? So of course, if the remainder happens to be 0, in other words, that numerator there is 0, so that term there doesn't really exist, what we say is p of x perfectly divides f of x, and the answer is just q of x, right? Another way of seeing that is if r of x is actually 0, in other words, there's no remainder, so this term here just goes away, so f of x can just be factorized into q of x and p of x, right? Now, this is how we can actually go from having something which is improper to having something which is proper. So this thing here may well actually be improper. But the fact is this thing here is always going to be proper. This is always going to be proper. And why is it going to be proper? Because the degree of r of x is actually always going to be less than the degree of p of x. Okay? And you might say to yourself, well, why is that the case? And my simple answer would be try some long divisions, just take some numbers, and you'll find out that the remainder can never actually be bigger than the thing you're dividing by. Because if the remainder happens to be bigger than the thing you're dividing by, then what you can actually do is you can do another step of the division and then make that thing smaller. Okay? So the fact that we have this beautiful relationship means that we have a way of being able to use just the definition of what a fraction is, in other words, division, to be able to convert something which is improper to something which is actually proper, and then this function here is just going to come along for the ride, really, right? So let's take a look at some examples, and we can start to see how all this works and fits together. So example one gives us a nice fraction, and we have to express this in partial fraction form. Now, off the bat, the thing to notice is the numerator is actually of order 2 and the denominator is actually of order 2. So this is actually technically top heavy. So we can't just apply the standard things that we've seen in the previous video on partial fractions. So we have to be able to express this from being a top heavy to being actually just a regular fraction, right? So to be able to do that, I've got to expand the denominator and actually do the division. So I'm just going to write the numerator out as it is. I'm going to expand the denominator to say it's going to be x squared and then plus 2x minus x. So it's going to be plus x and then minus 2. That's my denominator, and then at this stage I want to be able to go away and sort of do long division. So I'm going to just do that on the side here. So I've got 2x squared plus 3x plus 4. That's what we're dividing, and we're dividing by x squared plus x minus 2. So of course long division is a fairly standard part of the AS syllabus or the first year A-level maths. So I'm just going to go through the motion here and write out each of the terms, and then subtracting this just gives me that, and then 3x minus 2x is just x, and 4 minus minus 4 is actually 4 plus 4, which is x plus 8. So I can come here and using the generic form I wrote down last time, which if I recall correctly is f of x over p of x, is actually going to give me q of x plus r of x over p of x, where we know that the r of x has to be of a lower degree or order than p of x. So in this case, what we have is 2 plus x plus 8 divided by the denominator I had, which is x squared plus x minus 2. And that makes perfect sense because 2 happens to be my quotient. My remainder is obviously x plus 8. And then that's the thing I was actually dividing by. And of course, this is not top heavy anymore, right? The numerator was actually of a smaller order than the denominator. So now all we have to do is we just have to express this fraction here on the right-hand side into partial fraction form. And once we've done that, we would have managed to express the entire thing on the left-hand side as partial fraction form. So we can just do that as a separate calculation in itself. So I'm just going to say I want to express x plus 8 over that sort of x squared plus x minus 2, but obviously it's better to express it in the factorized form because we want to be dealing with sort of partial fractions, of course. So I'm just going to write that down, x plus 2, and referencing the stuff that we did at the start of the video and obviously in the previous video on partial fractions, I know the partial fraction generic form in this case is just going to be x minus 1 plus b over x plus 2. Then at this stage, we basically apply the ideas that we sort of developed or worked through last time, which is we sort of combine things to be able to have a common denominator, x minus 1, x plus 2, and then we can sort of say, actually, we better have x plus 8 better be identical to everything in my numerator. So x plus 2 plus b x minus 1. And at this stage, because we have an identity, we can just start to basically either equate coefficients or it's easier to put in values, right? Because this expression is true for all x, so I can just pick some x to be able to make this easy for me. So I can say put x equals say minus 2, and when I put minus 2 in, the left hand side becomes 6, and the right hand side, well, minus 2 plus 2 goes to 0, so a times by 0 just gives me 0, so a just goes away. And then when x is minus 2 in the second term, I get minus 3b. And then that tells me that actually b is equal to minus 2 indeed. So we've got a value for b, and similarly we can say put x equals 1, and when we put 1 in, the left-hand side becomes 9, and the right-hand side becomes 3a, and then the x minus 1 actually becomes 1 minus 1, which goes to 0, so b times 0 is just going to give me 0, so we don't have to worry about the b. And this tells me that my a actually happens to be 3. So our answer, since we've actually worked out the values for a and b, is as follows. So we go back to sort of this expression here at the top, and we know that this thing here, x plus 8 over x squared plus x minus 2, can actually be written in this form. So I just put the 2 down first. So I do that directly. And then I say, well, what's my a? My a is 3, so it's going to be 3 over, and then the denominator has to be x minus 1, because I have an x minus 1 there. And then the other thing is a b, and my b is minus 2, so I'm just going to say minus 2 over x plus 2. and we've done this question. So let's quickly just check our answer. So let's try and undo what we just did. We just figured out that was our answer. So let's try and now combine this and see if we actually get back the top heavy fraction that we actually started with. So what I'm first going to do is I'm just going to say, well, let me just combine sort of these two fractions here, right? So they're a slightly harder thing to work with, so I'm just going to say 2, and then I'm going to get a common denominator, so it's going to be 3 times by x plus 2 minus 2 times by x minus 1, and then the denominator is obviously going to be x minus 1 times by x plus 2. Right? And then at this stage, we can sort of come here maybe and say, well, the 2 is just going to be there, and the numerator is going to expand to give me 3x plus 6 minus 2x plus 2, and then the denominator is just going to be x minus 1, x plus 2. And we can simplify the sort of numerator a lot more because the 3x minus the 2x is just going to give me the x, and the 6 plus 2 is actually going to give me the 8, which is beautiful because that looks very much like the thing that we actually did the partial fraction calculation on. So the only thing we now have to do is just combine the thing that we're actually left with here. And again, we're going to apply the exact same trick. We're just gonna combine the entire thing with a sort of with a common denominator. So I'm just going to have that, and I'm going to have x plus 8, and I'm going to have overall it's going to be x minus 1, x plus 2. So looking at the numerator, the quadratic is going to expand to give me x squared, and the denominator is obviously also going to expand out if I wanted to expand it out to give me the exact same quadratic. However, when we started with our function, we did not have it in the expanded form, so we need not really expand this, and we can just leave it in the factorized form, right? I have expanded the top because I want to get it closer to a form that we actually started with. So I'll leave that, and then sort of at this stage, what we have is simplifying this, we get, obviously, there's only one x squared term, which is 2x squared, but then these two x terms are going to combine. The 2x and the x is actually going to give me the 3x, so plus 3x, and then the minus 4 and the 8 is going to give me the plus 4, so I get plus 4. And then the whole thing obviously is over the very denominator that we've actually had all along. And at this stage, we actually get the exact same thing that we wanted to initially express in partial fraction form, and it is obviously top heavy, so we've got the right answer. So let's move on to the next example. So for example 2, we have another top heavy expression, top heavy fraction that we've got to express in partial fraction form. It's going to be the exact same thing as we've already done, so let's just jump in. Of course, before I can actually do anything to this in terms of being able to express in terms of partial fraction form, what I've actually got to do is I've got to get it from a top heavy improper to actually something that's proper. So we're going to have to do division. So I just say x squared plus 3, and we're dividing by x squared minus 4, and of course we're going to marry up the squares, and there's only one of those are going to go in, so I'm just going to have x squared minus 4, and when I do the subtraction, I get nothing here, and then the 3 minus 4 is actually a 7. So using the exact same idea of what we said last time, f of x over p of x can actually be expressed in the form as q of x plus r of x over p of x, where in our case our q is going to be 1, so I actually write down the 1. Of course, our f is x squared plus 3 and our p is x squared minus 4. Then our remainder is of course 7, so because it's a positive 7 I say that, and the function we're dividing by is x squared minus 4. So all that now remains to be done is for 7 over x squared minus 4 to be expressed in partial fraction form. So maybe I can do that as a separate calculation on the side. So we say 7 over x squared minus 4, and this is where we've got to go back to our knowledge from the previous video. So since we want partial fraction form, the first place to start would be to actually get the proper sort of factors of the denominator, and of course it's the difference of 2 squared, so we can write that as x plus 2, x minus 2, and then using sort of standard ideas, we can just say that has to be, the partial fraction form has to be a over x plus 2 plus b over x minus 2, right? And again, we can combine this to say, well, the common denominator is going to be x plus 2, x minus 2. So we're actually going to have this sort of thing. And the entire reason we did this was so we can have the denominator to be x plus 2, x minus 2. But now that we have this, we can actually go on and say that we better have 7 being identical to a x minus 2 add b x plus 2. And at this stage, I prefer to just sort of substitute. So I said take x equals, say, 2. So when we put 2 in, the left-hand side is just 7. We get a times by 0 plus b times by 4, which actually tells me b is 7 over 4. And similarly, we say take x equals minus 2, and we get the left-hand side is just going to be 7, but we're going to get a times by minus 4 plus b times by 0, and that then gives me a actually just being minus 7 over 4. So in other words, for this sort of thing here, for x 7 over x squared minus 4, the partial fraction form for us turns out to be minus 7 over 4 over x plus 2 plus 7 over 4 over x minus 2, right? And a slightly nicer way of writing it might be if I actually swap these around. So I write this term first instead of this term afterwards, just so I want the positive in front. I can say 7 over 4x minus 2 minus 7 over 4 x plus 2. But of course, we're not quite done because that's not our full answer, because the function we wanted to express in partial fraction form is here, and we know we can write it in that sort of form, and we've only so far expressed that in partial fraction form. So I've got to basically put this result into that, and then I'm done. So the overall answer is as follows, which is x squared plus 3 over x squared minus 4 is actually identical to 1 plus 7 over 4 x minus 2 minus 7 over 4 x plus 2. Let's now quickly just go and check to make sure this makes sense. We're going to do the exact same thing as we did last time. So let's just combine the sort of the more complicated looking fractions. So I know that we're just going to have one's going to come along for the ride, and then the denominators are almost sort of exactly the same. And in fact, this 7 over 4 is common to both the fractions. So the nice thing might be to take the 7 over 4 out, and then to just have 1 over x minus 2 here minus 1 over x plus 2 here, right? And that might be a lot more easier to be able to combine this. So I get 1 plus 7 over 4, and we get a common denominator, so we get x plus 2, and then we take away x minus 2. Of course, the takeaway sign here is that sign there, which we have to keep, and then the denominator is just x plus 2, x minus 2, right? And now simplifying the numerator, we just get 1 plus 7 over 4. That's going to be ever present. The numerator is going to be x plus 2 minus x plus 2, right? And the denominator is obviously x plus 2, x minus 2. So at this stage, we see that very, very nicely the x's are going to cancel, so we can just get rid of the x's. And we also see that the two 2's are going to combine to be able to give me a 4. So what we actually have is we have 1 plus 7 over 4, and then we have a 4 on top here, and we have obviously the x plus 2 and the x minus 2, like so. So here, given that the fraction that we started with this time, the denominator was not in factorized form, the denominator was in expanded form. So I am going to expand the denominator. I'm going to write everything else out, and I'm going to put a multiplication sign there. And because of the difference of two squares, it's just going to give me x squared take away 4, right? And then there was a 4 in the numerator. And again, we see here the 4 in this denominator is going to cancel with the 4 in that numerator. So actually, the entire fraction that we're dealing with, I better write in black, the entire fraction that we're actually dealing with is is much better simplified to just give me 7 over x squared minus 4. And now we're nearly home because all we have to do is just express this as one fraction. So again, we take the common denominator of sort of x squared take away 4, x squared take away 4. So the first thing I wrote down is now overall just 1. So we have that. And then finally combining this, we can say it's the same thing as x squared take away 4 plus 7 over x squared take away 4, which of course the minus 4 plus 7 is actually nothing other than plus 3. And here we have it, we get the exact same thing as the fraction that we started with. So again, this is perfectly sensible. Example 3, we have an even more complicated looking expression. Again, it is top heavy. That's the entire purpose of this video. So let's just jump in and try and write this in partial fraction form. So to begin with, we have to express this in a form where it's actually not top heavy. So it's actually a proper fraction. So I'm just going to write down the expression that we already have. So it's 4x cubed plus x squared. To be able to write this in a more sensible way, I'm going to have to do the long division. So I'm going to write down the thing I'm going to divide by first in this case, just to make sure I don't make a mistake. And then I'm going to write down the thing that I'm actually going to be dividing. So it's going to be 4x cubed, and then it's going to be x squared minus 16x plus 7, and both of these are cubics, so I see that a 2 will actually do the job quite nicely in the quotient here, and I'm going to get 2 multiplied by everything in that bracket, so it's going to give me 4x cubed minus 8x squared plus 4x, right? And then we sort of take away, and once we take away, we get no x cubes, and we get 9x squareds, and we actually happen to get negative 20 lots of x, and of course the plus 7 is going to remain there. So again, at this stage, I can sort of go back, and now I'm just going to write down the standard form without sort of doing too much explaining here, because we've already seen that done a lot of times. So it's going to be 20x plus 7, and then obviously that's going to be over 2x cubed minus 4x squared plus 2x. So all we have to do is just be able to express this fraction, which is not top heavy anymore, as a partial fraction. So to be able to do that, of course, we have to be able to factorize the denominator. So let's just take a look at this monstrosity. 2x cubed minus 4x squared plus 2x. There are lots of even terms here, so we can straight away factorize out a 2x, and that just gives me an x squared and then minus 2x, and then I actually get a plus 1. And of course, I can also factorize the quadratic. It's a fairly standard sort of quadratic to factorize, and in fact, it's a complete square. Okay. So once we have that, I can actually come here and say this is exactly the same as 2 plus. So let's now just do the standard sort of arguments that we actually apply to that sort of thing. 9x squared minus 20x plus 7 over 2x x minus 1 squared. And the standard partial fraction form here is going to be a over 2x. Remember, we've actually got a squared in the denominator, so we've got a repeated factor, and these things must be expressed in this sort of way. So I'm going to have one of those factors, and then I'm going to have two of those factors, right, as follows. So as before, we get a common denominator, so we just say a times by x minus 1 all squared times by 2x times by x minus 1, and then finally c is just going to be times by 2x. And the denominator, of course, the whole point is we're going to get 2x x minus 1 all squared. So once we've actually got that, we can simply just say, well, the numerators must be identical. So I must have 9x squared minus 20x plus 7 better be identical to a multiplied by x minus 1 squared plus 2bx x minus 1 plus 2cx. Okay, so we again turn to our standard trick of just putting in numbers, because we know the identities is going to be true for all values of x. So we say take x equals 0. So the minute we take x equals 0, the left-hand side of our identity just gives us 7. So we get 7, and the right-hand side of our identity, we see that there's an x there and there's an x there, so both the c and the b are going to get killed, and 0 minus 1 is minus 1, but the whole thing's being squared, so it's just going to be negative 1 squared, which is 1. So we've actually already got a value for a, right? So we've got a value for a, so now let's take x to be 1. So we take x to be 1 because then that term gets killed and that term gets killed, and we just end up with 2c, right? And the left-hand side obviously gives us 9 minus 20 plus 7. And 9 minus 20 plus 7 is actually just going to give me minus 4. So I get minus 4 is actually equal to 2c, which actually tells me that my c better be minus 2, right? So we've worked out the value of c. So now we've just got to work out the value for b, but we can now just take x to be negative 1. So when I put negative 1, I'm just going to get 9 times negative 1 squared, which is 9. Negative 20 times negative 1, which is positive 20. So 9 plus 20 is going to be 29. And then the plus 7 is actually going to give me 36. So the left-hand side actually gives me 36. But the right-hand side, when I put negative 1 in, I get negative 1 take away 1, which is negative 2. But negative 2 squared is just 4. So I'm going to get 4a. 4a. And then I'm going to have plus, it's going to be negative 1 times by negative 2, which is actually just 2. And then that 2 times by the 2 in front is actually going to give me the 4. So it's going to be plus 4b, and then it's going to be negative 2c. And this can be easily solved because we know what the value for A is, and we also know what the value for C is. Once we put them in, we can actually work out the value for B, and B actually works out to be a nice number, which is actually just 1 in this case. So we actually have our values for A, B, and C, and we can now put those in and actually write down our answer. So let's make a bit of room and write down the answer. So in the interest of time, I've just written out what the answer is going to look like. This is the thing we started with, and we were able to express it in sort of this sort of a form, where the thing on the right-hand side is now is a proper fraction. And then we figured out that actually, once we write it in partial fraction form, that A, B, and C happen to be 7, 1, and minus 2 respectively. So we can put that in, and this is basically our answer. This is our answer in sort of partial fraction form. And there's a quick check that I've written out. I've not filled in the details, but perhaps you can spend a bit of time looking at this yourself if you're not convinced that this answer is correct. That when you actually simplify the entire thing on the right-hand side here, you do actually get the thing we started with. And of course, all I've done in going from the left-hand side here to the right-hand side here is actually just expressed everything as a common denominator. Yeah, you can check the details. Let's take a look at the last example. So we again have the sort of things that we've already been seeing. The only point which is actually worth mentioning here is the denominator was a little bit interesting because the x plus 1 cannot, x squared plus 1, sorry, cannot actually be factorized, which means that all the steps are going to be pretty much the same. We're just going to have to sort of think a bit more harder about that. So let's get started. So let's write down the thing that we're actually got to deal with. So it's 22 minus 17x plus 21x squared minus 4x cubed, and then the denominator, because this fraction is top heavy, we're going to have to divide it. So let's expand the denominator. We're going to get x cubed minus 4x squared plus x, and then take away 4, right? So once we've got that, so let's write down the thing we're going to divide by. We're going to divide by x cubed minus 4x squared plus x, take away 4. That's what's going to be doing the division. And then the thing being divided is going to be the thing on the top, which is, I better write this the other way around. So I better write it with the cube first, and then the square, and then the x, and then the constant. So I'm going to say minus 4x cubed plus 21x squared minus 17x, and lastly plus 22, right? So once we have that, again, standard long division from year 1 of the A-level syllabus, I want to get these two the same, so I'm going to have to multiply the thing in bracket by minus 4 to get minus 4x cubed. And then minus 4 times 4 is 16, so I have 16 lots of x squared. 4 times negative 4 is, sorry, x times negative 4 is minus 4x, and negative 4 times negative 4 is actually 16, so that's how many constant terms we have. And we take all this away, and upon taking away, we realize that we've got no x cubed. That's precisely why we picked negative 4. And then 21 take away 16 is actually 5. So we have 5 lots of x squared. Negative 17 take away 4x, or negative 17x take away negative 4x is actually going to give me negative 13x, and 22 take away 16 is of course nothing other than 6. So basically what we've done is, again, we've started with some function in the numerator, we've divided it by some polynomial in the denominator, and we've managed to get a quotient, and we've managed to get a remainder, but of course the remainder still needs to be divided, right? So in this case our q happens to be negative 4, so we write that down, and then our remainder happens to be this quadratic here, so we write that down. It's going to be 5x squared take away 13x add 6, and then the denominator is of course going to be the function we were already dividing by, so that's our x cubed take away 4x squared plus x take away 4. And it is worth pointing out, as always, that the numerator is actually of order less than the denominator. So the fraction we've managed to get on the right hand side is actually a proper fraction, but because we want to express this in partial fraction form, we better factorize its denominator. So I'm going to write down the numerator as it was, and then I'm going to re-express the denominator in the factorized form, which we already know is x minus 4 times by x squared plus 1. Right, so x minus 4 times by x squared plus 1. Now at this stage we just go away and we deal with that proper fraction as a thing in its own right. So we write down 5x squared take away 13x add 6 over x minus 4 and x squared plus 1. So if we recall how we were writing down general partial fraction forms, in this case, because the x squared plus 1 cannot be factorized, the thing I've got to have as a general partial fraction form is got to be a linear function on the top and the quadratic that I've already got on the bottom, right? With that out of the way, then we just apply the standard set of arguments. We combine the thing we've got to have a common denominator. So we're going to have x minus 4 x squared plus 1, and of course the numerator is a times by this denominator, and then bx plus c times by x minus 4. So I'm gonna write that down, plus bx plus c times by x minus 4, right? So unsurprisingly, we're going to equate numerators of the thing on the extreme here and the thing on the extreme here, right? And we're going to be able to get an identity. So we're going to say we better have x to the 5x squared, sorry, minus 13x plus 6 be identical to a multiplied by x squared plus 1 plus bx plus c, and that has to be times by x minus 4. Now, we can equate coefficients and get simultaneous equations, but let's not do that. Let's instead just pick values in a systematic way. So let's just take x to be 4, because then the b and the c are going to die, right? So I'm just going to end up with take x equals 4, and what that does for me is I actually have 5 times by 4 squared, but 4 squared is 16, and 5 times 16 actually is 80 if I'm not mistaken. And then we have 13 times by 4. Well, 4 times 10 is 40, 3 times 4 is 12, so 40 plus 12 is 52. So we have 52, and then the 6 just comes along for the ride, and the right hand side becomes the x squared is going to give me 16, and then plus 1 is 17, so I get 17a, and the entire reason for choosing x equals 4 was so that bx plus c could actually die. So we just have the thing we've already got, and upon simplifying this, we just get 86 take away 52 is actually 17a, but 86 take away 52 is 34, which is equal to 17a, which actually tells us that a is actually 2. So we've actually got a value for a, and we can now go back and say take x equals 0 in this case. So when we take x equals 0, then the left-hand side clearly is just going to be giving us 6, because all the x terms are going to die. And the right-hand side, well, 0 plus 1 is just 1, so we just get an a, But then the other thing, we get b times by 0, so the b dies, the c remains, but then 0 minus 4 is just minus 4. So the b is going to die, and the c is going to get multiplied by minus 4. So I'm actually just going to get minus 4c. But we already know what a is. We know that a is actually 2, so we're going to get c being a minus 6 divided by 4, sorry, which actually happens to be minus 4 over 4, which actually gives us minus 1. So the only thing we've got to work out is perhaps a value for b. So let's write that here. We've got a bit of space here. So we say we can now just pick any x value at all. Well, we could have always picked any x value, but in this case, what I'm trying to say is there isn't a special x value we can pick to kill the c but not the b. So we could, so we just take x equals say 1. That's easy enough. The left hand side just becomes 5, take away 13 plus 6, but the right hand side becomes 2a, and then it becomes plus minus 3 times by b plus c, right? And since we already have a value for a, and we also already have a value for c, then we can sort of start to put those in, and then we'll have a linear equation just in terms of b. And once we do all of that, actually that tells us that the value of b works out to be 3. Okay, so we've effectively done the entire question. Let's just write down the answer in full and end the video. So putting everything together, we see that since we know a is 2, b is 3, and c is minus 1, and we also showed that the thing we were trying to express in partial fraction form was going to have the form minus 4 plus a over x minus 4 bx plus c over x squared plus 1, we can put in the values of a, b, and c, and we get that the initial improper fraction that we actually had has the partial fraction form minus 4 plus 2 over x minus 4 plus 3x minus 1 all over uh, x squared plus 1. With that, I'd like to bring this video to an end. I hope you found the content of this video useful. If you did, please hit the like and subscribe buttons, and do let us know, as always, in the comment section as to what you would like to see more videos on. Thank you for watching, and we will see you in the next video.